Hello, this is the first video for Graphs and Networks Series 3 on further graph theory for OCR Discrete Further Mathematics and introduces the colouring argument for bipartite graphs. In previous series we've introduced bipartite graphs. So they are graphs where the nodes are in two distinct sets, noting that no arcs between any members of the same set. So every edge then connects a member of the first set to a member of the second set. Here is an example in the diagram below. You'll note that a complete bipartite graph is denoted by KRS, in which there are R vertices in one set and S vertices in another. We can make the diagram into a complete bipartite graph K43 by adding more edges. So the edges in this set have to connect completely to all the edges in the other set. So noting that complete bipartite graphs KMN has m times n arcs, there should now be 4 times 3 or 12 arcs on that diagram. We now introduce colouring a graph. A proper colouring of a simple graph is the assignment of a colour to each vertex such that no two adjacent vertices have the same colour. We'll note that by adjacent vertices we mean a pair that are joined by an arc. Now we want to find the fewest colours to do this. A graph is what we call k-colourable if each vertex can be assigned one of the k colours so that adjacent vertices get different colours. This graph is 3-colourable. Let's see if we can reduce it to being 2-colourable. Well, if we start here and say, alright, that's going to be red, and then the adjacent vertices are blue, then that one's okay with blue. So let's also make that one blue. In which case, this one would be alright as red. But then we have a problem here. And also along this arc here, because we've got two adjacent vertices, both blue, and we wouldn't know which colour to make that second green one. Therefore, we've confirmed that we do need 3 colours for this particular graph. A colouring argument may be used to show that a given graph is, or is not, bipartite. So here is a small bipartite graph laid out in 2 very obvious sets, and there are no arcs within the sets, so therefore we could easily make these ones blue and these ones red. This implies that all bipartite graphs are 2-colourable. Also, if we consider a 2-colourable graph, then this must mean that all one colour only join to the other colour. In other words, that there are 2 sets, and therefore that the graph must be bipartite. Sometimes bipartite graphs are much larger and drawn less clearly than this example here, so the colouring argument can be used to help decide whether a graph is bipartite or not. You do not need to learn algorithms, as they will be given in the question or formula book in the exam. However, it is useful to be aware of this common colouring algorithm as given below. So step 1 is to choose a vertex and colour it with colour 1. Step 2, if all the vertices are now coloured, stop. Otherwise, use a second colour to colour all the uncoloured vertices for which there is an edge that joins your initial vertex in colour 1. Step 3. If all the vertices are coloured, now stop. Otherwise, go and use colour 1 to colour all the uncoloured vertices for which there is an edge that joins the vertices now of colour 2. Step 4 is the iterative step where we go back to step 2. In this example, we need to apply the colouring algorithm to determine whether or not it's a bipartite graph. Let's start with A, and we'll do that in blue. That means then that C will be in red, and so will E, which would then imply that D must be blue, and B must be blue, moving on from E, and that F might be blue. However, we have some issues here, because we can see that D and B are joined by the arc and of the same colour, and so are E and C. So even one of those examples is enough to show that it is not two colourable, and therefore it is not bipartite. In this second example, we are again asked to find if it's bipartite, and we'll do that by looking to see if it's two colourable. In this particular form, which it might well be an isomorphic form of a more obvious bipartite graph, we can look to see where the difficulties may lie. Well, AC is okay, and AD is alright. So is AE. If we look then at, say, BE, those colours work. BG, CF, DF, and FG. And making sure that I don't forget GA. If I wanted to check that I hadn't forgotten any arcs, I could look at the order of each of the nodes and add those all up. 18, and then I need to divide by 2 to get the number of arcs, bearing in mind that counting the order counts every arc twice. I have indeed checked all 9 arcs, and therefore I can say that this is two colourable, and therefore it is a bipartite graph. This is easily confirmed by moving it around in GeoGebra to see if I can show an isomorphic equivalent being a bipartite graph. So if I move G across to be with all the other reds, notice the arcs are moving with it. So I'm just creating different isomorphic versions of the same graph. And if I move those, you can see then that this two sets clearly form bipartite graph. In the next video, we'll investigate Hamiltonian graphs.